Late in the summer of 1977, an historic mission of exploration was launched. Twin spacecraft, christened Voyager 1 and 2, broke free from the Earth's gravity on journeys to the outer reaches of the solar system. Their primary destinations were the four giant outer planets: Jupiter, Saturn, Uranus, and Neptune. For 13 years, the Voyagers probed these mysterious worlds at close range, while collecting data and transmitting stunning images back to Earth. Among thousands of pictures of planets and moons, perhaps the most memorable was recorded on February the 14th, 1990, when Voyager 1 approached the edge of the solar system, then turned back toward the Sun. With its wide and narrow-angle cameras, the spacecraft captured unprecedented views of our home star and 6 of its orbiting planets. One of them appeared as a small pale dot, engulfed by a ray of sunlight. It was the Earth, from nearly 4 billion miles away. While the world gazed intently at this pinpoint of light, timeless questions about its meaning, purpose, and significance suddenly took on new relevance. And once again, as in ages past, we paused to consider our planet's role within the grand scheme of the universe. The mystery of the Earth's significance in the universe has challenged philosophy and science for more than 2,000 years. Early perceptions were shaped by the work of the Greek scholars Aristotle and Ptolemy. They taught that the Earth sat motionless in the center of the heavens while the moon, sun, and other stars and planets revolved around it. This geocentric view was the foundation of Western cosmology for 18 centuries. Then, in 1543, the Polish astronomer Nicholas Copernicus ignited a revolution. In his book on the revolutions of the heavenly spheres, Copernicus argued that the Earth was not stationary, but instead orbited with the other planets around the Sun. For the first time, a correct understanding of the mechanics and structure of the solar system was in sight.
The idea of the moving Earth seemed to violate some fundamental principle, but Copernicus somehow had the mental power to imagine what even to him seemed absurd. So he thought the impossible. The Earth moves. And once you imagine the Earth moving instead of the Sun, the mathematics of that cosmic machine started to make sense. It was the key that unlocked one of the great mysteries of the universe.
Copernicus had laid the cornerstone for modern astronomy. Yet, 400 years after his discovery, the empirical fact that our planet was not the center of the solar system had evolved into what is now known as the Copernican principle. The idea that the Earth occupies no preferred place in the universe.
Copernicus had a theoretical way of explaining the apparent motion of the planets across the sky. That's all it was. It wasn't a theory that told us whether or not Earth was special, or whether we played some importance in the scheme of things, or whether every place in the universe was the same as every other place. Nevertheless, this reinterpretation of Copernicus became prominent in the 20th century. It's often called the principle of mediocrity. This principle says that our location and our status are mediocre, they're unexceptional. As a result, we should not assume that we are in any way privileged or that the universe was designed with us or beings like us in mind.
The Copernican principle and the concept of the Earth's insignificance was popularized during the 1970s and 80s by the late astronomer Carl Sagan. In his best-selling book, Pale Blue Dot, Sagan wrote,
"Because of the reflection of sunlight, the Earth seems to be sitting in a beam of light, as if there were some special significance to this small world. But it's just an accident of geometry and optics. Look again at that dot. That's here. That's home. That's us. Our posturings, our imagined self-importance, the delusion that we have some privileged position in the universe are challenged by this point of pale light. Our planet is a lonely speck in the great enveloping cosmic dark."
One reason for the widespread acceptance of the Copernican principle can be traced to a discovery made on this mountaintop overlooking Los Angeles. Between 1921 and 1926, the astronomer Edwin Hubble used this telescope to make some of the most important discoveries in the history of science. Through the window of the Mount Wilson Observatory, Hubble unveiled the true magnitude of the universe.
At the time that Hubble was doing his work, many astronomers believed that the galaxy, our galaxy, marked the edge of the universe, and there was nothing beyond it.
Edwin Hubble altered this perception of the universe when he used the most powerful telescope of his day to photograph indistinct objects in space. Long thought to be nearby clouds of gas and dust, Hubble determined that these patches of light were actually individual galaxies, many as large or larger than our own Milky Way.
The implication in what he found was that the universe consists of, indeed, billions of galaxies, each with many billions of stars and planets. And it was a universe with a wealth of numbers and variety that transcended the imagination of both layman and astronomer. He, in effect, enlarged the boundaries of the universe.
Edwin Hubble revealed that the Milky Way galaxy, encompassing more than 100 billion stars, including our sun, was a mere pinpoint of light in the universe.
When Hubble found that there were many galaxies, we saw that our galaxy was nothing distinguished at all. Just one
Edwin
ordinary
Hubble's
galaxy.
discovery. Yet today its profound implications still evoke a fundamental question. Does contemporary scientific knowledge actually confirm the Copernican principle's primary claim, that the Earth and the life it sustains exist without purpose or significance in the universe? An outgrowth of the Copernican principle is the belief that habitable planets and complex life are abundant throughout our galaxy and the rest of the cosmos. Perhaps no scientific endeavor has been influenced more deeply by this idea than the research program called SETI.
Well, SETI, which is, of course, the search for extraterrestrial intelligence, is trying to do exactly that. We're searching for extraterrestrial intelligence. In other words, we're looking for aliens that are at least as clever as we are. Now, we try and do that not by trying to go there the way they do in the movies all the time, or waiting for them to come here. We try and find the aliens, if you will, at home on the basis of eavesdropping on signals they might be sending our way. So we use large telescopes pointed at other star systems to try and find these telltale signs that there's some cosmic company out there.
Since 1960, SETI researchers have utilized radio telescopes throughout the world to monitor transmissions from distant regions of the Milky Way. While no definitive signs of intelligent life have ever been detected, these investigations have triggered much speculation about the possibility of extraterrestrial civilizations.
Estimates vary all over the place. Carl Sagan thought there might be millions of civilizations that are kind of contemporaries of ours. I can imagine that within the Milky Way galaxy, the number of contemporary intelligent civilizations, I think, is probably in the thousands, maybe hundreds of thousands. But the bottom line, actually, when people ask, well, why do you think that they're out there, is that the universe is extraordinarily rich, extraordinarily vast. The number of stars that we can see is on the order of 10,000 billion star systems. So unless there's something very, very special, miraculous, if you will, about our solar system, about our planet Earth, unless there's something extraordinarily unusual about it, then what happened here must have happened many times in the history of the universe.
The assumption that habitable planets and extraterrestrial life are abundant has inspired not only the SETI program, but also the new science of astrobiology and the search for biological evidence of living organisms, past and present. Since 1995, this search has extended beyond our solar system, as astrobiologists have identified more than 100 planets orbiting nearby stars. Each of them is a gas giant, much like Jupiter. While few scientists believe that these alien worlds can sustain even simple life, their discoveries represent important steps toward answering a question that will shape astronomy in the 21st century. Are habitable planets rare or common in the universe?
I'm an astrobiologist, and the area that I've done the most work in lately is the field of extrasolar planets. What motivates me is just to examine the conditions necessary for life and look elsewhere in the universe and see if those conditions are met anywhere else. And the answer could be yes, and the answer could be no, and either answer is interesting.
Guillermo Gonzalez works as a research scientist in NASA's astrobiology program. His interest in this field is tied to his early fascination with the prospect of life beyond the Earth.
I grew up in the 1960s, and like most other people of my generation, I was really amazed by the Apollo lunar landings, and that really inspired me and had something to do with my getting interested in astronomy. In my early years, I came to believe very strongly that there must be other civilizations out there and that the galaxy was teeming with life. And so I was a strong supporter of the search for extraterrestrial intelligence. My belief wasn't based on any real hardcore scientific arguments. It was just the impression that I had that the galaxy was such a big place. And I didn't give the other side of the equation much thought. In other words, there's two sides of the equation. There's the number of stars, the number of trials, if you will. But the other side is the factors. It takes a lot of factors to have a habitable planet in a planetary system.
For Gonzalez and other astrobiologists, these factors, required for the Earth's habitability, became the focus of extensive research.
We've demonstrated in dozens of different ways the laws of physics and chemistry that pertain in a laboratory anywhere on Earth apply anywhere in the solar system, apply anywhere in the galaxy, and in many cases out to the most distant galaxies that we can see.
There are indeed unchanging physical laws in the universe that apply to the entirety of the universe, that they're not localized to one place.
This consistency in the laws of physics and chemistry has led many researchers to conclude that the factors necessary for complex life on Earth are also the best parameters in the search for habitable planets elsewhere in the universe. Most serious discussions about these factors begin with the same prerequisite: liquid water.
All the searches that are being done for life elsewhere, their starting position is a terrestrial class planet with water.
It is now widely recognized that the chemical properties of water are exquisitely suited for carbon-based life. These properties include water's ability to dissolve and transport the chemical nutrients vital to all living organisms, and its unmatched capacity to absorb heat from the sun. a process critical for regulating the Earth's surface temperature. In liquid form, water is an extraordinary substance, and its existence hinges upon another factor essential to complex life: a planet's distance from its home star.
It's like what they say in real estate: location, location, location. A habitable planet lives in what we call the Goldilocks zone. It's not too hot, it's not too cold, it's just right. And when I say just right, I mean just right for water.
Liquid water really helps define the habitable zone. If it's too hot, again, the water just boils away. You just can't get condensed water. It's too cold, as in Mars today, it freezes out.
Within our solar system, the habitable zone is relatively narrow, beginning well outside the orbit of Venus and ending short of the orbit of Mars. If the Earth were just 5% closer to the Sun, it would be subject to the same fate as Venus: a runaway greenhouse effect with temperatures rising to nearly 900 degrees Fahrenheit. Conversely, if the Earth were 20% farther from its home star, carbon dioxide clouds would form in its upper atmosphere, initiating the cycle of ice and cold that has sterilized Mars.
The presence of liquid water is a necessary condition for life, but it's not a sufficient condition. After all, there may be liquid water under the frozen surfaces of Mars and Jupiter's moon Europa, but there's very little chance that complex life is. You see, contrary to what the Copernican principle might suggest, the recipe for life is much more complex than just add water.
If a recipe for a planet capable of supporting complex life really did exist, then what ingredients beyond liquid water might be required? The list of necessary factors continues to grow.
We live on this paper-thin crust. If the Earth's crust were significantly thicker, then plate tectonic recycling could not take place.
The Earth's crust varies in thickness from about 4 to 30 miles. It consists of more than a dozen tectonic plates that are in constant motion. This dynamic geology regulates the planet's interior temperature, recycles carbon, mixes chemical elements essential to living organisms, and shapes the continents. Deep within the Earth's interior, the movement of liquid iron generates a protective magnetic field essential to complex life. If our planet was smaller, its magnetic field would be weaker, allowing the solar wind to strip away our atmosphere, slowly transforming the Earth into a dead, barren world much like Mars.
We need an oxygen atmosphere, and the oxygen-nitrogen atmosphere that the Earth has is necessary for complex life.
As seen from space, the Earth's atmosphere glows as a thin blue ribbon of light. Measuring less than 1% of the planet's diameter, it is composed of a mixture of nitrogen, oxygen, and carbon dioxide. As a result, our atmosphere ensures a temperate climate, protection from the sun's radiation, and the correct combination of gases necessary for liquid water and complex life.
For a size of planet like Earth, our moon is big. The current thinking is that if our moon didn't exist, neither would we.
1/4 the size of the Earth, the moon's powerful gravitational pull stabilizes the angle of its axis at a nearly constant 23.5 degrees. This ensures relatively temperate seasonal changes, and the only climate in the solar system mild enough to sustain complex living organisms.
If we find life out there, especially complex or even intelligent life, it will be around a star similar to our own.
We orbit what is known as a spectral type G2 dwarf main sequence star. It is well suited for our needs. If the Sun were less massive, like 90% of the stars in the galaxy, the habitable zone would be smaller. To remain within its boundaries, the Earth would have to be positioned closer to its star. Here, increased gravity would lock our planet's rotation into synchronization with its orbit. While one side of the Earth continually faced the Sun and increased radiation from solar flares, the dark side of the planet would lay shrouded in perpetual cold and ice. It is unlikely complex life could tolerate these drastic extremes in temperature.
A lot of things went right on Earth to have yielded complex life, absolutely.
The number of factors that have been postulated has grown. Currently, the typical number you would see is, in a typical list, would have something like 20.
We find that we need to be at the right location in the galaxy, that we're inside the circumstellar habitable zone of the star, that we're in a planetary system with giant planets that can shield the inner planets from too many comet impacts, that we're orbiting the right kind of star that's not too cool or not too hot, that we're on a planet that has a moon that can stabilize the tilt of its axis, that we're on a planet that's a terrestrial planet, a planet that has a crust that's just thick enough that it can maintain plate tectonic activity, but it has enough heat in its interior that it's still circulating its liquid iron core so it can generate a magnetic field, that it has an atmosphere that has enough oxygen to allow for complex organisms to survive, that it has enough water and enough continents to allow for the diversity of life or an active biosphere that you need to support complex creatures such as ourselves. All these factors have to be met at one place and time in the galaxy if you're going to have a planet as habitable as the Earth, which you need for complex and even technological life.
In an attempt to estimate the probability of attaining this combination of factors simultaneously, some researchers have developed equations assigning a conservative 1 in 10 value to each factor deemed necessary for advanced life.
If every element has to be there at the same time, you have to multiply the probabilities, and that's what makes the probability at the end so small. You've got 10% of this and 10% of that, and these things rapidly multiply to exceedingly small numbers. The numbers on the order of 10 to minus 15, which is 1/1000th of 1 trillion. And it's a number like that that you have to compare to the 100 billion stars that are in the galaxy. 100 billion is a very large number, but 1,000th of a trillionth is much, much smaller. On their face value, these probabilities are speaking. What they're telling us is this can't happen, or this is very unlikely to happen in the galaxy. And that's where the evidence is pushing us.
There are many probabilistic resources in the galaxy, but on the other side of the coin are all these factors that you need. You have to get just right in order to have just one habitable planet like the Earth. And that leads me to conclude that yes, we're rare in the galaxy.
While a growing body of scientific evidence may support this hypothesis, does the possibility that our planet is rare within the galaxy imply anything about its significance? Recently, astronomer Donald Brownlee considered this question in the best-selling book Rare Earth: Why Complex Life is Uncommon in the Universe.
There's a general feeling that nature wants to make Earth-like planets, and that naturally that life will evolve on them and naturally evolve to something like us. And yet the conditions, the environmental conditions on the planet that would allow more complex creatures similar to people, or plants and animals, is very rare. And so we wrote the book Rare Earth to point out that the Earth is actually a rather special place.
Brownlee contends that while relatively simple microbial life may thrive on planets throughout the universe, planets capable of sustaining complex life are exceedingly uncommon.
Well, the entire universe is highly hostile to life. If you compare all the known places in the universe, none of them compare to Earth. We live in a very special environment that provides what we need, provides air, provides food, stable conditions, so that the Earth is almost like a giant organism where its systems are interacting in a way that allows animals to survive. The real question is, why does Why did this happen? Was it just a matter of luck or not? If you look at thousands of planets, only a small fraction of them, very small fraction, will be truly Earth-like. So if we are very rare, we did win the cosmic lottery. So we're a lucky planet. We're just in a very fortunate place. We are very rare, we did win the cosmic lottery. So we're a lucky planet. We're just in a very fortunate place.
When you consider chance as an explanation for a planet like Earth, you have to look at it in the context of the universe as a whole. While the odds appear astonishingly small that you'd get all the right ingredients to support complex life at this one place in the galaxy, you have to keep in mind that our galaxy is just one of perhaps 100 billion galaxies in the observable universe. Still, logically, I think you have to ask yourself, what if this convergence of factors didn't come about as the result of simply a cosmic lottery or a mere fluke or luck, but what if it's the result of some larger underlying purpose or design? And if the Earth does exist for a purpose, is there any way that we could tell?
On October the 24th, 1995, a rare natural phenomenon unexpectedly triggered a unique search for an answer.
Oh, look at this guy! It started with an experience I had in 1995. I went to observe a total eclipse of the sun in India. It was my first and still only total eclipse of the sun. It was a spectacular event. It's just an experience for all the emotions. Either astronomers who can understand the whole phenomenon and can predict it to within a second of time anywhere on the Earth, or a local native, are equally in awe and reacting in the same way to this incredible phenomenon. It really left a big impression on me.
For 51 unforgettable seconds, Guillermo Gonzalez and thousands of others looked on in wonder at this rare astronomical event. Gonzalez would later reflect upon both the mysterious beauty he had witnessed in the North Indian skies and the factors that had made it possible.
Fabulous! Fabulous! The requirements for producing a total eclipse of the sun are a luminous body, in our case the sun, an eclipsing body, in our case the moon, and then an observer platform, in our case the surface of the Earth, and they all have to be in a straight line in space. The apparent size of the moon in the sky has to be almost exactly the same as the apparent size of the sun in the sky. They're both about half a degree. The sun is 400 times bigger than the moon, but it's 400 times further away. So there's this coincidence people have noted for centuries, but they just say, oh, well, it's a coincidence, and shrug their shoulders.
As Gonzalez examined this rare alignment of sun, moon, and Earth, he recognized the importance of these celestial bodies to the existence of complex life on our planet. The gravitational pull exerted by our moon, for example, is strong enough to regulate the Earth's climate by stabilizing its tilt and helping to circulate the warm and cold waters of its oceans, while our planet's distance from the sun permits both liquid water and an oxygen-rich atmosphere.
You have to have the right distance of the observer's home planet from its host star, and you have to have a large moon, and so there's this very strong overlap between the requirements for producing eclipses and the requirements for habitability, for having a planet that can support life.
In 1999, Gonzalez described this relationship between our survival and our ability to observe solar eclipses in the journal Astronomy and Geophysics. His ideas intrigued philosopher Jay Richards.
I've been focusing my research in cosmology, and in particular on applying probability theory to the fine-tuning of the laws of physics. I had a strong sense that this evidence pointed towards some sort of wider purpose to the universe. Then I read Gonzalez's work, and I had the same feeling that he did, that perfect solar eclipses were sort of the tip of the iceberg, the first instance of an entire class of evidence that provides a way for judging if the universe is the result of a fluke or some impersonal process or the result of purpose or design.
In the summer of 1999, Gonzalez and Richards initiated a program of joint research. They began their study by considering a characteristic of solar eclipses little known outside the scientific community. These striking events are not only compelling to observe, they also open a portal onto the physics and chemistry of the entire universe.
Really, you can think of eclipses as a giant natural experiment set up that allows us to observe a part of the sun that's critical towards understanding how its light is produced in its atmosphere.
The fact that the Earth is going around the sun and the moon is around the Earth, and the sizes and the distances between the Earth and the moon and the sun are just so to give you a perfect solar eclipse is a wondrous thing, because it allows us to measure the constituents of the upper layers of the sun's atmosphere.
During a solar eclipse, the moon fits so perfectly over the sun that it shields its blinding light, providing astronomers with a view of the star's atmosphere otherwise impossible to experience. At the moment of totality, the pinkish arc of the chromosphere, the atmosphere's innermost layer, becomes visible, and with it a rainbow-like band called the flash spectrum appears when the sun is viewed through a prism. The eclipse of 1870 led to an understanding of the structure of the sun's chromosphere and the discovery of helium, the second most abundant element in the universe.
The spectrum is probably the single greatest source of information about a star. And it was during a couple of historic eclipses in the 19th century that astronomers figure out how the spectrum of the sun is produced. And they only were able to figure it out because of the particular circumstances during a total eclipse.
These circumstances are both precise and crucial. If our moon was slightly larger, it would partially block our view of the chromosphere and diminish its spectral light. A smaller moon would allow too much light from the sun, destroying our view of the solar atmosphere and the flash spectrum.
And so you have to have a nearly perfect match between the sun and the moon, so you don't hide the chromosphere. And that insight afforded by eclipses in the 19th century is what finally permitted astronomers to figure out how the spectra of distant stars are produced. Really, that opened up stellar astrophysics and allowed us to understand how other stars work, because distant stars, after all, are other suns.
The relationship between eclipses and scientific discovery was also revealed in the spring of 1919. On May the 29th, research teams headed by British astronomer Arthur Eddington photographed the sun and adjacent stars in the Hyades star cluster during the darkness of totality. Later analysis of the pictures verified that the sun's gravity bent light from distant stars traveling toward the Earth at the angle Albert Einstein had predicted. Einstein's theory of relativity, an idea that revolutionized our understanding of the universe, had been confirmed during a total solar eclipse.
And that experiment was only possible because the stars become visible during a total eclipse. They're very important in the history of science. And the best place in the entire solar system to view solar eclipses is from the surface of the Earth. I've actually calculated the circumstances for eclipses from all the other planets and all the other moons, about 65 of them, the major moons. And it's an amazing coincidence. The one place that has observers is the one place that has the best eclipses.
Between the factors necessary for complex life and scientific observation. But was this merely an isolated fluke of nature, or a glimpse at a principle and a purpose fundamental to the universe as a whole?
That was the million-dollar question that we continually had before us. What if those things that make a planet habitable also make that planet the best place for making scientific discoveries? That is, what if those rare locations in the universe that are compatible with observers like ourselves are also the best places overall for making observations?
For 3 years, Richards and Gonzalez meticulously tested their idea against evidence gathered from a wide range of scientific disciplines. In the 2004 book, The Privileged Planet, they published their hypothesis. The same narrow circumstances that allow us to exist also provide us with the best overall setting for making scientific discoveries.
In the book, we detail more than a dozen examples of this correlation between life and discovery. And these aren't quirky, marginal examples. Each treats a condition critical to its respective scientific field. Some deal with remote things, like the nature of galaxies. Others are much closer to home.
While a perfect solar eclipse was the catalyst for Gonzalez and Richards' hypothesis, their observations would never have been possible without another, more familiar example of the correlation between life and discovery: the atmosphere of the Earth.
It's striking when you see pictures of the Earth from the Apollo missions or other spacecraft, and you see this very thin layer of the atmosphere surrounding the Earth that sustains all the life that we know on Earth. And so you need a certain mix of elements to support a complex biosphere like ours. Not just any atmosphere will do.
Our appreciation of the Earth's atmosphere has increased significantly during the last 40 years as exploratory spacecraft have probed the solar system. These missions have confirmed that within the Sun's family of more than 70 planets and moons, the Earth is one of 7 bodies enveloped by a thick canopy of gas. Yet among these 7, only the Earth's atmosphere can sustain complex life. And only the Earth's atmosphere is transparent.
It's an atmosphere that's made up of mostly oxygen and nitrogen with very little carbon dioxide and very little other carbon compounds or atoms in the atmosphere that gives you a transparent atmosphere. If we had too much carbon in the atmosphere, we get hazes, organic hazes in the atmosphere, like you see on the large moon Titan, for example.
The dense shroud of gas that blankets Saturn's largest moon resembles the atmospheres surrounding Neptune, Uranus, Saturn, Jupiter, and the greenhouse cauldron of Venus. None of these alien worlds know the stars, or even offers a clear view of the sun.
Now, of course, if you were suddenly transported to Titan or Venus or to one of the outlying gas giant planets, the lack of a clear view of the universe wouldn't be much of an issue because you'd be dead. But that's precisely the point. If we're right, if the conditions for habitability and scientific discovery appear in the same places, then you're going to get conditions like you do on Earth, an atmosphere that sustains complex life like ourselves and also enables scientific discovery of the universe around us.
The virtues of such an atmosphere are continually tested. As the Earth moves through space, it is bombarded by radiation from throughout the universe. This radiation is emitted by the Sun and other celestial objects, including supernovas and distant galaxies. It reaches our planet in wavelengths described as gamma, X-ray, ultraviolet, visible, infrared, microwave, and radio. Together, they comprise the electromagnetic spectrum. Almost all of these wavelengths are invisible to the eye and either lethal or useless to organic life. Yet within this spectrum of frequencies, a thin sliver of radiation proves essential to plants, animals, and human beings.
In other words, there's really just a very narrow part of the electromagnetic spectrum that's going to be useful for living processes like photosynthesis. It's not as if life could have evolved to use gamma radiation or X-ray radiation or something like that. There's really just a narrow part of the spectrum that would be useful to life processes. Well, as it turns out, that's also the same narrow part of the spectrum that is the most informative about the various structures that we discover in the universe around us.
These specific frequencies that enable plants to manufacture food and astronomers to observe the cosmos represent less than 1/trillionth of a trillionth of the universe's range of natural electromagnetic emissions. Fortunately, it is the type of light our sun produces in abundance, and that most easily penetrates the filtering shield of our atmosphere to reach the surface of the Earth.
It's a remarkable coincidence that the kind of atmosphere that's needed for complex life like ourselves does not preclude that life from observing the distant universe. It's a surprise. It's something that you wouldn't expect just chance to produce. Why would the universe be such that those places that are most habitable also offer the best opportunity for scientific discovery.
In 1997, Guillermo Gonzalez began a study of the Earth's specific location within the Milky Way galaxy. It would eventually lead him to more evidence of a correlation between life and discovery.
Just as our location in the solar system is optimized for habitability, so is our location in the galaxy. We inhabit a spiral galaxy, which means it's highly flattened. It has a spherical bulge in the center and has spiral arms. And we live about halfway between the center of the galaxy and the edge.
Working closely with astrobiologists Peter Ward and Donald Brownlee, Gonzalez compared our position in the Milky Way to other regions within an often hostile galaxy.
The galaxy has a lot of dangers, and perhaps the most dangerous place in the galaxy is the galactic center.
Well, in the center of the galaxy, this density of stars is very high, and there are more supernovas and stuff. And there are things that could harass life right in the dead center regions of our galaxy.
You also have the giant black hole at the very center of the galaxy. And if it were to have a close encounter with a star passing near it, it would rip it to shreds and form an accretion disk around it and emit lots of radiation, particle radiation and electromagnetic radiation, gamma rays, X-rays.
While a black hole, exploding stars and deadly radiation would make complex life virtually impossible near the galactic core, the outer edge of the Milky Way poses other challenges to habitability.
In the outer regions, the situation is much more subtle. We live on a planet made out of iron, magnesium, and silicon, and oxygen. If we went in the more distant regions of our galaxy, out towards the outer edge, the abundances of these elements are lower.
There probably aren't enough heavy elements to build Earth-sized planets that can support life. So there's a happy median between the dangerous galactic center and the outer edge of the galaxy.
Gonzalez, Brownlee, and Ward labeled this region, where complex life is possible within the Milky Way, the galactic habitable zone. Their theory was first published in 2001 and has since received growing acceptance among astrobiologists.
There's a lot more research that needs to be done to determine just how wide the habitable zone is, but I think there's general agreement that yes, there are definitely places in the galaxy that you cannot have civilizations because they're very dangerous, and there are places where you just have a very low abundance of heavy elements.
While these obstacles to habitability are minimized far from the core and edge of the Milky Way, Gonzalez has also identified large areas within the galactic habitable zone itself, which are less hospitable to complex life.
Even within the habitable zone in the galaxy, it's broken by the spiral arms, which are dangerous places. That's where most of the supernovae go off in the galaxy. That's where the star formation is taking place.
We don't want to be too close to a spiral arm. We want to be outside the spiral arm at about the right region of the galaxy.
It appears this is precisely where the Earth is located, in the relatively safe and uncrowded region between the Sagittarius and Perseus arms of the Milky Way.
Location is everything, and so we occupy that special place in the galaxy where habitability is optimized, threats are minimized, and we have enough building blocks to build an Earth.
Guillermo Gonzalez and Jay Richards have conducted research on another facet of the galactic habitable zone. They now argue that the Earth is also located in the best setting within our galaxy for astronomical research.
As it turns out, our position in the universe is not only critical for life, but it's also surprisingly important for making scientific discoveries. We're located near the midplane of the galaxy, a very highly flattened galaxy, between spiral arms in a region with very low dust extinction. While we are in the plane of the galaxy, that does not obscure a large part of the sky, so we can have very clear views.
For more than a century, this nearly ideal platform of observation has enabled astronomers to study the structure of the Milky Way. Looking toward the constellation Sagittarius on a clear night, for example, we see that the stars in our galaxy are not uniformly distributed across the sky. Instead, they appear as part of a concentrated band, a flattened disk of stars, dust and gas, 100,000 light-years in diameter.
The Milky Way band in the night sky is us looking edge-on into the plane of the galaxy. If we were living in the center of the galaxy, things would look much more spherically distributed. And so it would be very hard to distinguish things that are inside the galaxy from things that are outside. And it's also very dusty, much dustier towards the galactic center than it is in our region. And so the views of the distant universe will be much more difficult to obtain. They'll be much more compromised.
Similar problems would exist for astronomers working on a planet located within any of the galaxy's spiral arms. Here, denser concentrations of dust clouds and gas illuminated by stars would make it difficult to determine the shape of the Milky Way, or to distinguish the stars in our galaxy from the rest of the universe.
On the surface of the Earth, we're really in the optimum position for seeing both the nearby structure of the Milky Way galaxy as well as seeing the distant cosmos as a whole. So once again we see that the best location for habitability and for producing a habitable planet is also the best overall position for scientific discovery, in this case at the galactic scale. For centuries, the fact that we can discover things about the universe has really been something of a mystery. Why would beings like ourselves be able to discover a universe like this? Why is what we think about the universe, why would it correspond to the way things really are?
Our ability to discern and understand the universe is a fundamental part of what makes the universe tick, so that we're linked into it. This isn't just a sort of an accident, a trivial little byproduct. It is something that is linked to the great cosmic scheme of things. Now, I've no idea how that linkage works, why it's there, or anything of that sort, but I'm very, very struck by the fact that we can understand the universe in such exquisite detail and at such a deep level.
The spectacular progress of modern astronomy and physics is the product of a universe accessible to the human eye and mind. It is a universe governed by laws and forces that literally hold our planet Earth and the entire cosmos together, and are finely calibrated to allow for both complex life and scientific discovery.
If you didn't have something like gravity that pulled matter together, you would never get planets, you wouldn't get stars, you wouldn't get any complex organisms. If you didn't have the strong nuclear force, there would be nothing to hold protons and neutrons together in the nucleus. And so you wouldn't have any atoms, so no chemistry. If you didn't have the electromagnetic force, you would have no bonding between chemicals. You'd have no light, and the list goes on. So you need all these sorts of fundamental principles have to be in place in order for life to occur. Wipe out one of those principles, wipe out one of those laws, no life.
During the past 40 years, scientists have determined the relative strengths of each of these primary laws and forces. These strengths are so critically balanced, they are often described as being finely tuned.
If you're to take the basic fundamental constants of nature and you were to change these even slightly, or you were to pick their values at random, you would almost never get a universe that would be habitable in any sort of way. That is, you couldn't have galaxies, you couldn't have planets, you couldn't have complex biological organisms if these fundamental constants were even slightly different, slightly stronger, slightly weaker than they actually are in this universe. That's the idea of fine-tuning.
To better appreciate this concept, imagine a machine able to control the strengths of each of the physical constants. If you changed, even slightly from its current setting, the strength of any one of these fundamental forces, such as gravity, the impact on complex life would be catastrophic.
If you increased it by a little bit, no large-scale life forms could exist. Anything that was more than the size of a pea would be completely crushed. So you might be able to get life of a very, very primitive sort, such as bacteria, but you could never get conscious observers.
This is one of a long list of properties in underlying physics that seem to be prerequisites for a universe with life. For example, the strengths of the other forces are all important, the masses of the various subatomic particles. If all of these things were even a little bit different, then life, certainly life as we know it, could not exist.
These forces and constants are another example of the correlation between life and discovery. For not only are they finely tuned for our existence, they can also be understood.
It's remarkable how well the laws work. And not only that, it's remarkable how simple they are. And that also is related to the discoverability of the laws.
Albert Einstein wrote, "I have deep faith that the principles of the universe will be both beautiful and simple." For nearly 400 years, scientists have discovered an elegant simplicity in the mathematical equations that express and unlock the laws of the cosmos.
It's been said that many of the most important theories in theoretical physics can be written on a single sheet of paper. And this, I think, ought to be considered surprising, that such a simple formula or equation could have such far-reaching applications to a very complicated and very large universe.
What you have is a universe that is not only finely tuned for life to occur, but also has a beautiful, elegant mathematical structure, and a structure such that we can discover that structure.
Most scientists just take it for granted that the world is both ordered and intelligible. And the intelligible parts I find really quite extraordinary, because it's one thing to accept that the universe is ordered, but ordered in a way that human beings are capable of understanding is an extraordinary thing. And so the question naturally arises, what is the explanation for that?
Many who have pondered this mystery of an intelligible universe argue that it cannot be easily explained away.
From naturalistic assumptions, you would not expect the universe to be understandable by human reason. After all, within the standard naturalistic story, human reason was developed to be able to hunt prey, get around in the everyday world, attract mates.
We have certain skills, for example, we can jump streams and catch falling apples and so on, which are necessary to getting by in the world. But why is it that we also have the ability to discern, for example, what's going on inside atoms or inside black holes? These are completely outside the domain of everyday experience, totally surplus to requirements, not at all necessary for good Darwinian survival.
Discoverability of the universe is something we didn't need for our existence. It's something additional to it. It seems then that whatever the source of the universe is, it intended that it contain observers who can discover.
You put observers in the best places for observing. That is, if you're going to do things intelligently, that's what you do. The nature of our planet, the nature of its atmosphere, the location in the solar system, the type of solar system it's in, even the type of star that we're around and the location within the galaxy are optimal for making a wide range of scientific discoveries. It turns out that those are also all the most important conditions for a habitable planet, that is, for a planet that's conducive to beings like us and without which we could not survive. I think that's just the sort of pattern that ought to suggest to people conspiracy rather than mere coincidence.
There's something about the universe that can't be simply explained just by the impersonal forces of nature and atoms colliding with atoms. And so you have to reach for something beyond the universe to try to account for it.
Such an approach lies at the foundation of modern science. In his search for a more elegant description of the solar system, Nicholas Copernicus was motivated by his desire to comprehend what he called the mechanism of the universe, wrought for us by a supremely good and orderly creator. The system, the best and most orderly artist of all, framed for our sake.
And so he imagined this analogy of a workman, a craftsman, making something that worked well and was beautiful. And that analogy, it wasn't one of his conclusions. That analogy was one of his assumptions.
The founders of modern science, like Copernicus and Kepler and Galileo and Newton himself, believed that the universe was the product of a mind, that it was intelligible to beings like ourselves because the universe itself was the product of an intelligent being.
They were driven by this notion that this was essentially a theological quest. They were uncovering God's handiwork in the way the world worked. I mean, what a thought that we can glimpse the mind of God. We can actually figure out how God put the universe together. There's a hidden subtext in nature which can be exposed through this procedure we call science.
Though most scientists no longer think in such explicitly theological terms, recent evidence may again point to an Earth far different from the contemporary image of a pale blue dot lost in a cosmic sea.
We've often been told, especially in the 20th century, that the universe does not have us in mind. That is, that we exist in a very large universe and that the universe was not designed for beings like us. We are simply life that happened to come about on a tiny little planet surrounding a tiny insignificant star in a run-of-the-mill galaxy within a very large universe that was not intended. Our argument suggests something completely different. It suggests that the universe was intended, that the universe exists for a purpose, and that purpose isn't simply for beings like ourselves to exist, but for us to extend ourselves beyond our small and parochial home, to view the universe at large, to discover the universe, and in fact, perhaps, to consider whether that universe points beyond itself.
As we gaze ever deeper into the universe, we are inevitably drawn back to timeless questions. What is the source of the cosmos? And what is our purpose within it? While answers will always be debated, valuable new insights are now at hand, emerging from a corner of the universe where complex life and scientific discovery have converged on an extraordinary planet called Earth.